Next, let's learn the first cache line placement policy, which is called direct mapped cache. Recall that the simple example that we learned in the introduction to cache lecture was a direct mapped cache. And basically, for direct mapped cache, for any cache line in the memory, there is going to be one and only one frame in the cache that is going to be used to store this cache line. Or more accurately speaking, there is only one frame in the cache corresponds to a cache line in the memory. So let's look at an example, an illustration of how this mapping works, how this direct mapped cache works, by how it maps the address of a cache line to a frame in the cache. Let's say this is our memory. Again, we draw the memory as frames, as cache lines. So we're gonna have a lot of cache lines here, and this is our cache line index, from 0, 1, 2, and all the way goes down. And here we have our cache. And these are going to be our frames. And each frame is going to be used to store a cache line. Let's assume that we have totally 2 to the n frames. Totally 2 to the n frames. And for each frame, we can also give it a frame index. So it also starts from 0, 1, 2, goes down all the way to n minus 1. 2 to the n minus 1, since we have 2 to the n minus 1 frames. So the last one index is 2 to the n minus 1. We have them 2 to the n frames. So for the mapping of the cache line in the memory to the frame, the mapping algorithm is very simple. We just map 0 to 0, map frame 1 to 1, map cache line 1 to frame 1, and we're gonna map cache line 2 to frame 2. So it goes all the way down. For the frame that is located as for the cache line with an index 2 to the n minus 1, it is going to be mapped to the last frame, the 2 to the n minus 1 frame in the cache. And then for the next frame, for the next cache line in the memory, for the cache line 2 to the n, is going to be again mapped back to the beginning of the frame of the cache. So it's going to be mapped to the frame with the index of 0. And then for the next cache line 2 to the n plus 1, is going to be mapped to the frame with an index 1. So we're going to repeat this process until we have computed, we have the address frame index for all of the cache lines in the memory. So this mapping is very simple. We just continuously map the cache lines in the memory sequentially to the frames in the cache cache. And mathematically, we describe this mapping using this equation. So essentially, the mapping algorithm or the mapping equation is the frame index that is going to be used to store a cache line is effectively going to be the cache line index. Is going to be the cache line index modulo the size of the cache, which is 2 to the n. So the math is very simple. We just take the cache line index modulo 2 to the n, the size of the cache, the number of frames in the cache, then we get the corresponding frame index that is used to store this cache line. And additionally, as one last thing that I want to mention is for a cache with 2 to the n frames, the effective size of this cache is 2 to the n multiplied by 2 to the s, the size of each frame, the size of each cache line, or the size of the data in each frame. So it's 2 to the 6 bytes. So the size of this cache is 2 to the n plus s. This is the size of the cache in terms of bytes. And this does not only apply to direct mapped cache, it is also this particular equation also applies to any caches. As we have discussed previously, to determine the index of the frame that is used to store a cache line, all we need to do is perform a modulo operation. Essentially, we're gonna take the index of that cache line and modulo over the size of the cache, the number of frames in the cache, then we get the frame index. However, how do we actually compute this modulo operation in the hardware fast enough? Let's first look at an example of decimal numbers to see how can we compute this modulo operation fast. Say we have a simple decimal number 789. If we want to compute 789 modulo 10, how do we do this? Because this is the decimal number and the base of this number is 10, so 789 modulo 10 effectively can be computed by taking the last digit, and write it as the answer. So 789 modulo 10, effectively the answer is going to be 9. All we need to do is just to take the last digits, because this is a decimal number, its base is 10. So modulo over 10 is effectively just take the last digit out, and it gives us the answer. Similarly, if we want to do 789 modulo 100, we can rewrite 100 as 10 to the 2. 789 modulo 100 is effectively can be computed by taking the last 2 digits of this number out. So the result is going to be, this is 9, and so the result is going to be 89. And similarly, if we want to do 789 modulo 1000, 10 to the 3, all we need to do is take the last 3 digits out. So the result is going to be 789. In summary, if we have a number x, decimal number x, and we want to do a modulo operation over 10 to the n, all we need to do is extract the last n digits of x, and it will give us the modulo operation result. We can do exactly the same thing for binary numbers. Assume that we have a binary number y, and we want to do a modulo operation of y over 2 to the n. All we need to do is to extract last n bits or last n digits of y, and it can give us the result. For example, if we have a binary number 45 and we want to, this is binary number, this is a decimal number. Let's say we want to modulo 45 over 2 to the 4, which is effectively 16. And all we need to do is to take the binary format of 45, which is 0b 101101, and modulo 2 to the 4. All we need to do is take the last 4 digits, which is give us the result 011101. If we do this math using binary numbers, 45 modulo 2 to the 14 is effectively 45 modulo 2 to the 4, which is effectively 45 modulo 16. It's going to give us, the result is going to be 13, which is exactly 1101. This number that you can, which is exactly this binary number. Therefore, for binary number, if we want to do a modulo over 2n, all we need to do is extract the last n bits out. Finally, recall that we already partitioned the address of an arbitrary data into two parts. Assume this is the address of a piece of data, and this is the address of a data of any piece of data. We already partitioned it into two parts. The first part is going to be S bits. The first part has S bits, the last S bits of this address, and we already call it as the offset of this piece of data, the offset of the location within within cache line location of this piece of data. We call the first part of it as the cache line index, right? We call the first part of it as the cache line index. And to compute which cache line that is supposed to be stored is the cache line that has this data, all we need to do is really just take this cache line index here, the first few bits of this address, and do a modulo operation. And as we have discussed, the modulo operation effectively equals to extracting the last n bits off. So all we need to do, for the modulo operation, all we need to do is to extract the last n bits off, and we can get the frame index for this piece of data, the index of the frame that should be used to store the cache line that contain this piece of data. So here, this n bits directly corresponds to is the frame index. Is directly the frame index. For the rest of the bits of this data, the rest of these bits, they will be used as the tag of the cache line. Recall when we were discussing the components within the components of the frame, we say that there are at least 3 components. The first one is the data of the cache line. The second one is the status bits. The second component contains all the status bits, and the last component of a frame contains the identifier of the cache line that is stored in the frame. And we say that we're actually going to use the address of the cache line being stored in there as the identifier. And in practice, we do not need to store the whole address of the cache line. Since for the cache line the offset does not really, since for the cache line being stored in the frame, the offset does not really matter because the beginning address of a cache line are always going to be 0. So we know that these bits are always going to be 0 for a cache line, for address of a cache line. And we know that these bits, wherever that a cache line is going to be stored in a frame, they are going to have the same frame index. So for any cache lines that are going to be stored in the same frame, they're going to have exactly the same frame index, which means that they are going to have the same frame index, which means that they're going to have the same n bits. So the only difference between the cache lines that are going to be stored in the frame is going to be the first few bits of this address. Therefore, we'll only use the first few bits of the address of a cache line as a tag. So in this way, we partition the address into 3 parts: the offset of that piece of data, which indicating that which exactly piece of data within the cache line that we're actually going to access, which word inside the data that we are going to access. And then the second part is designated. The second n bits are going to be used as the index of the frame, is going to be used to compute the index of the frame that is used to store the cache line that contains this piece of data. And finally, the rest of the bits are going to be used as the tag to identify the cache line that contains this piece of data. In summary, the mapping process and the internal component of a direct mapped cache can be described with the following figure that I'm going to draw. First, let's draw the cache here. Here we're going to have the cache. gonna have the cache, which is gonna have a number of frames, right? You have a number of frames in the cache, and each one, this our frame index. This time I'm drawing it on the right side because I need the left side for something else. So this is our first frame, this is our second frame, and the third frame, frame 2. And there are 2 to the n frames. Eventually the last one is going to be 2 to the n minus 1. And this is our frame. And within each frame, we're actually going to have 3 components at least. The first one is going to be the tag of the frame, the tag of the cache line that is stored within the frame. The second one is going to be the status bit, indicating whether it is valid or not, or whether the cache line has been written or not, whether it's dirty or not. And the last part is going to be the data. Therefore, given a arbitrary piece of data that is going to be accessed or going to be stored in the cache line, let's figure out how do we locate that piece of data in the cache. So let's say this is the address of data that is going to be accessed. Let's figure out how do we determine whether this piece of data is in the cache or not. And as we have discussed previously, we partition this address into 3 parts. The first part is the offset. The second part is the frame index. And the last part is the tag. It's the tag of this piece of data. So the first thing, when we have this have this address, the first thing we're gonna run it over a hardware component. We're gonna take the frame index and over a hardware component. Its name is called a decoder. And this decoder is effectively used to select a corresponding cache line. So this decoder is directly connected to, has a line connected to any of the, is connected to each frames in the cache. And when a frame index is input into the decoder, one of these lines will be activated to select a cache line, to collect a frame that may have the data that corresponds to the data that may has the data that we want to access. So for example, in this case, let's say that this line is activated, and so the frame that corresponds to it will be selected. And this frame, again, it's going to have a tag, it's going to have status, and it's going to have data. So the status will be checked. When this frame is activated, the status will be checked to determine whether this frame has data or not. Let's assume that actually this frame has data and it's already passed the check. So the next thing that the hardware is going to do is going to read out this tag. Read off the tag of the frame of the cache line that is being stored in this frame. And then this tag will be compared with the tag of the data that is being requested. So it is take the tag that is stored in the cache line, the tag stored in the frame, with compare with the tag of the data that we want to access. And this comparison will tell us that if the data that we want to access is in the cache or not. If these two tags matches, if the tags match, which means that the data that we're requesting is actually in the frame, so this indicates that we have a cache hit. In the case we have a cache hit. However, if the tags do not match, indicates that in this case it indicates that we have a cache miss, and we need to draw in the data from the main memory. Now for simplicity, let's assume that this is actually a cache hit. When this access is a hit, the next what we need to do is to extract the data that is being requested from the cache line. Recall that the data stored in the frame contains all of the data within the cache line. And apparently, the cache line is much larger than we usually need. It's only usually 64 bytes, which is much larger than all of the functional units that we have in the CPU. Therefore, we usually only request a fraction, a small part of the cache. Therefore, the last thing that we need to do is to extract the data, extract the part of the cache line that is indeed being requested. We are usually going to request maybe a double or an integer from the cache line, so we do not really need all of the 64 bytes. So we're gonna read out the data, and then we're gonna send the offset of the data that is being requested. Here the offset indicates which part of the cache line that we're gonna read. So we send over the data, and we send over the offset. And then we use this offset to select the part of the data that is being requested. So we select the data from the whole cache line, the part of the data that is being requested from the whole cache line. Then we finally extract the requested data, and we're going to return this requested piece of data back to the processor, back to the CPU for computation.